Today we're going to talk about titration. Titration is using uh, a, a method to figure out how concentrated an acid or a base is. And we're going to use the concept of neutralization that we have been talking about earlier in the last chapters. And remember that neutralization occurs when the hydronium ions and the hydroxide ions are supplied in equal numbers by the reactants. So you wrote balanced equations in the past where you had an acid plus a base, and then in the process of them reacting, it formed a salt and water. So when the hydronium ions and the hydroxide ions are exactly equal in my balanced equation, then you have neutralized both the acid and the base. So the hydronium ion came from the acid, the hydroxide ion came from the base, and they will react with each other and they will end up forming water. Now let's take that concept and put some numbers to it. If 1 liter of a 0.10 molar HCl solution reacts with 1 liter of a 0.10 molar sodium hydroxide, in the equation of their reaction, there are in equal amounts, and so we say that they are present in chemically equivalent amounts. And the hydronium and hydroxide ions will combine, and when they are neutralized, the product of the hydronium ion and the hydroxide ion concentration will have a value of 1 times 10 to the minus 14, which we have been using several times already in this chapter. And in the process of neutralization, we said there's a salt, and if we're using hydrochloric acid and sodium hydroxide, we're going to end up forming a salt. The salt, the NaCl, is going to come from the sodium is going to come from this part right here. It's going to come from the sodium in sodium hydroxide, and the chloride is going to come from this part of the acid. This is a very common way that a salt forms. It takes the metal ion from the base and the non-metal or ion or the anion from the acid, and they combine to form the salt. So NaCl is going to be the salt that's produced in this reaction through neutralization, and this happens, we know from the past discussion, that HCl, hydrochloric acid, is a strong acid, and we also know that sodium hydroxide is a strong base. And when you have equivalent amounts of each, the resulting solution is going to be neutral. So the acid will have by itself had a pH of less than 7. The base had a pH of greater than 7. But when I put them together in equivalent amounts, the resulting solution is going to be neutral with a pH of 7. So this process of titration is a very controlled addition and the measurement of the solution of a known concentration, and it's required to react completely with a measured amount of a solution that we don't know the concentration. So we're going to very carefully add a solution that we know its concentration, and react it completely with a solution that's unknown in its concentration, and when they've completely neutralized, then we can use the measurements to calculate the concentration of the unknown solution. So the titration just provides a very sensitive means of determining when you have reached the chemically equivalent amounts. And we can do that visually by using indicators. Now, the point at which the two solutions used in the titration are present in chemically equivalent amounts, when we reach that point is called the equivalence point. We have given equivalent amounts of each, and when that point has reached, when the amount of each solution is equivalent, then we've reached what's called the equivalence point. Now, the point in a titration at which the indicator changes color, that's kind of a different thing than the equivalence point, but they are related to each other. But that point in a titration at which the indicator changes color, goes from one color to another color, and usually does it fairly rapidly over a change of pH. When you've reached that point, it's called the end point of that indicator. So we have the equivalence point that has to do with the amounts of solution, and the end point has to do with the color of the indicator. Now, indicators that undergo a transition at about 7, pH of 7, are used, as we learned in a previous discussion. We're going to use those to determine the equivalence points of reactions that involve a strong acid and a strong base. So they will end up being neutral because they're both strong. A strong acid, strong base, the middle of that is going to be a pH of 7. And the neutralization of strong acids with strong bases produces a salt solution with a pH of 7. So in other words, when I measure the pH of what's left, because the acids and the bases are used up and the salt is all that's left in the water, then this salt will have a pH in solution of 7. Indicators that change color at a pH lower than 7 are used to determine the equivalence point of strong acid and weak base titrations. This would be like hydrochloric acid reacting with ammonia, for instance. And in this situation, the equivalence point of this strong acid, weak base titration is going to end up being acidic. Not because the acids and the bases haven't used each other up, it's because the salt that's formed itself behaves as a weak acid. Now, indicators that change color at a pH higher than 7 are used to determine the equivalence point of weak acid, strong base titrations. This would be, for instance, if I were to take a weak acid like vinegar, acetic acid, and react it with like sodium hydroxide, which is a very strong base. And these reactions will produce a salt solution whose pH is greater than 7. So it's not that, again, that the acid and the base haven't been combined in equivalent amounts. It's just that the salt that's formed will make the salt solution will end up being on the base side. So it's because this salt actually that's formed itself is a weak base. So let's look at some of these titration curves. This would represent a curve where you are titrating an acid, hydrochloric acid in this example, with sodium hydroxide. So this is going to be a titration curve for a strong acid and a strong base. And in the lower left of this graph, we're starting out at a pH of 0. We haven't added any sodium hydroxide at all. Notice that across the bottom of the graph, we have moles of sodium hydroxide added. And at first, as we're adding sodium hydroxide to the acid, some of the acid is starting to be used up, and the pH of the solution that's in the flask is becoming less and less acid. It's headed towards 7. And as you get closer to the point where you have equivalent amounts, it starts to change a bit faster until when you are really close to the equivalence amount, the pH will very rapidly change in this region right in here, because you're going from just having a slight amount of acid left to having it all gone and slightly too much base. And then if you continue to add base, then the pH will continue to go higher and higher and higher towards 14. So this place right here in the middle is called the equivalence point. It's about halfway up this graph where it changes the most right in here. The equivalence point, we usually pick it at about at the midpoint. Now, if I were to react a weak acid and a strong base, then in my weak acid, and here they're using acetic acid, which is like what's in vinegar, so it's a weak acid. And notice that because it's a weak acid, and we start out with a 1 molar solution of this, the pH is not at 0, but it's up here between 2 and 3. And as I start adding sodium hydroxide to it, the pH, you'll notice, is changing much faster. And the reason why it's changing much faster is because, if you remember, acetic acid or vinegar is only a weak acid, which means it hasn't ionized very well. So there aren't a lot of hydronium ions in there. So the amount that's left will quickly decrease. And then again, when you get close to the equivalence point, the pH changes very fast in this range right here. And then as I continue to add base after the color has changed, then the pH will continue to go higher because sodium hydroxide is a strong base. So, but right in here, this equivalence point is where we say that we have had an exactly equivalent amount of acetic acid and sodium hydroxide. Now, the solution that contains a precisely known concentration of a solute is known as a standard solution. So in this previous two graphs, the sodium hydroxide was being used as our standard. We knew its concentration. Or I guess actually the acid was the one that we knew the concentration of. And we were trying to figure out what the concentration was of the base. Okay, so if you remember in the bottom of the left-hand corner of the graph, it did say 1 molar acetic acid or 1 molar hydrochloric acid. So those were our standard solutions. We knew their concentrations. Now, to standardize everything, and to know it with some certainty, we need to have another standard that we reference to, and that one's called a primary standard. And it's highly purified solid compound that's used to check the concentration of these solutions that I'm considering to be known. So when I order chemicals from the chemical company and I want something to be very precisely known what its concentration is, I will be ordering a primary standard. And from that, I can make other standard solutions. And the standard solution can be used to determine then the molarity of another solution by titration. So my standard could be an acid, it could be a base. It depends on which is it that I don't know. So we're going to now describe a process of carrying out a titration procedure. And we'll probably try to do this in a lab so that you'll be able to see this at work. And it says this following procedure is used to determine an unknown concentration of an acid solution. So in other words, the acid, we don't know its concentration, but we're going to titrate that solution with a standardized base solution. So the base concentration is known very precisely. And we have over on the right, we have these long skinny tubes. They're called burettes. And you're going to decide which burette will be used for the acid and which one will be used for the base. And then you would label one of those burettes so that you don't get confused. Because at the very end, we might switch back and forth between those, and we don't want to create problems for ourselves. And to begin with this, we're going to rinse the acid burette 3 times with acid. In other words, after we've washed it all out, we'll put some acid into it and rinse it out so that the only, quote, contamination, end quote, that it has in there is just the very acid I'm going to use. And we would do the same thing with the other burette with the base solution. So we kind of just rinse it out with whatever we're going to be using as our acid or a base. Okay, so then we're going to, the one that we've chosen to be the acid burette, we're going to fill it with an acid solution to the point that's above the 0 mark. So if you can kind of look at the middle section there, the left one, notice that they have the liquid level is higher than 0. So you can't read it in that range, but that's for a reason, because we want to remove all the air out of the tip. So as we open there's a little pip cut on the bottom of it, and as we open that, it's going to run some of the acid out, and so we can push out all the air bubbles, and we know that there isn't anything interfering with our ability to measure our volumes precisely. So we're going to release some of that acid into a waste flask, not the one that we're going to use, and we're going to lower the volume into the calibrated range. If you look on the second one of that middle section, you notice they've gotten it down into the between 2 and 3 milliliter range. And what you're going to do at this point is you're going to record the volume in that burette to the nearest hundredth of a milliliter. Now this burette has 10 markings in between, so it's to the nearest tenth. So you're going to try to estimate to the nearest tenth between 2 small marks. That's how you get to the hundredth of a milliliter, and then you will record that down as your starting point. Then you'll start with a new flask, and you're going to release a volume of acid, and that will come from your lab procedure that you're going to do, and you're going to release that amount of acid into your Erlenmeyer flask. And then when you've gotten that amount in there, you're going to record the new volume reading, and then you'll subtract that starting volume you had to find the volume of the acid that you've added. Because we need to know that amount precisely. Then we're going to pick an appropriate indicator, and we're going to put some drops in it. You only just need a few drops. As it says here, 3 drops is usually more than enough. And in this particular one, which is going to be a strong acid and a strong base, they've used, no, it's a weak acid and a strong base, sorry. They're going to use phenolphthalein for this indicator. Then you're going to fill your other burette, the one with the base, with a standardized solution of base to a point again above the 0 mark. And you're going to write down what concentration you know that base to be, because we need to know that later on to calculate how the concentration of the acid. And then you're going to again release some of the base into a waste flask so that the top of the liquid is down in the calibrated range again. Then you're going to record the volume of the base to the nearest hundredth of a milliliter as your starting point for the base. And then you'll put your flask underneath the base burette. Remember, in the flask you already have your volume of acid. And then you're going to turn the little petcop on the side and release some of the base into that solution. Notice that it says that the tip of the burette extends into the mouth so that you can kind of swirl it around without worrying that some of it's going to drip on the side. And as you put some base into the burette, you're going to constantly swirl it around. You're trying to mix the acid and the base and the indicator together. At first, you're going to notice that you're going to have a pink color right where the base drops into the acid, and that's because it'll be phenolphthalein is pink in a base, but as you swirl it around, the pink will go away because the acid and the base are reacting with each other, and we haven't used up the acid, so it'll still have the acid color. Then as you start getting close to the end point, the place where it changes color, then you want to start dropping it in more slowly, just drop by drop. One drop in, you'll swirl it around. Now, if you're getting close to the end point, one of the ways that you'll know you're close to the end point is that each drop, as it drops into the liquid that's in the flask, the pink color will last longer and longer until finally, in the middle picture there, the end point is reached, you're going to have a very light pink color even after swirling it for a long time. That pink color won't go away, which means you have reached the end point. So at that point, you're going to record your new volume and determine the volume of the base that's added. And then in the next section, we're going to talk about, okay, how can I take those numbers and determine the concentration of my unknown acid?